Hello and welcome back to AB1202 Statistics and Analysis Week 7 tutorial. Today we want to explore further the concept of confidence interval. So we're going to discuss what is confidence interval, everything about confidence interval, right? It's a formula, uh, definition, interpretation, and various uh, ways to calculate confidence intervals. Uh, the main question being, should I use T or Z? Okay, and then I want to also talk about more bread and butter issue for you. That is, what kind of questions will you be given in tests and quizzes? So two kinds of problems involving confidence intervals. Yeah? Okay, so let's get started. So the main thing is you must first acknowledge that we want to find population mean, right? So the goal is to find or calculate or estimate population mean as accurately and as cheaply as possible. So ideally, we want to know to infinite number of decimal places very, very accurately the population mean value. Now, of course, this mean value uh, can also be the population variance, population maximum, population minimum, and various ways to estimate them. Yeah. So to study them all will be very long-winded and complex. And what we want is to just focus on one particular number of the population, and that is the mu, the population mean. To do that, we will perform sampling, right? So we perform sampling because we uh, understand that we don't have infinite resources to measure every single entity, every single person, every single item in the entire population set. So we don't have the money, patience, manpower, technology, whatever, right? So it has to be down to the smallest, or rather the other way around, the largest number of sample size that we can afford. So we want n to be as high as possible, but the higher the n, the more expensive it is in terms of time, money, manpower, technology, sophistication, etc. So we will have to do a trade-off and find a suitable n, something that we can tolerate with the imprecision, but yet affordable. So that's important. And once we obtain sampling, to find mu, there are essentially two statistical ways to perform that estimation. Both are acknowledged as official, right? And they are acceptable not just in mathematics and uh, statistics, but also in the eyes of the law and the society. So um, essentially, confidence interval is one way, hypothesis testing is another way, right? In confidence interval, we want to put a range estimate around mu. So we're going to say, instead of saying point estimate, right? So instead of saying the population average height for the 200,000 people in the town, in the small town, is 1.6 because I measure my neighbor to the left and neighbor to the right. They are found to be 1.5 and 1.7. So we take the average, and that's 1.6. And I assert the 1.6 is mu, is the value of mu. Obviously, I'm going to be not accurate because nobody knows what is mu. So if someone were to challenge me and say yours is not accurate, then I would say, then you try. Give me your estimate, right? So if the person has enough resources, a lot of money, a lot of time, a lot of patience to calculate or measure every single person in that 200,000 people town, then sure, the person will be able to accuse me, right, of using a very tiny, small sample size and being inaccurate about it. Sure. But then typically challenging problems, they are challenging because the population size is really huge. No one, even if you have billions and billions of dollars, you don't really want to spend that money just to know one number super accurately. So the question becomes, what about you, right? If you say my sample size is too small, and if the other person also can only afford to measure two people, right, two random people, and that person takes another average, maybe 1.6 and 1.8, right, accidentally, and so he takes an average, and his estimate of mu is 1.7. And so everyone can have their own ways of calculating mu or point estimating mu. So those are one number. If you sort of imagine the one number point estimation, that exercise as shooting one arrow towards the bullseye, yeah, then confidence interval, which is more like a range estimate, is like shooting a little expanding net, right? That upon impact on the target board, it is not one arrow, but a little blob, right? So the area covered by that little blob or the little net will be your hit area. So that's more like an area kind of arrow. So the arrow is not a pinpoint arrowhead, but rather a arrow board or arrow punch, right? Something like that. So there's going to be a punch, a fist in front of the arrow, and that fist is completely flat in front. So where the fist face hits the target board, that is the entire area will help you to score points. All right, so that's the idea of confidence interval. Now, obviously, you can imagine the fist face can be huge, right? Then I use a big arrow fist face, so that one shot I can more or less cover almost everywhere of the target board. And suppose the game rule is that so long as any part of your fist face touches the bullseye, you get the bullseye. You get the highest mark, right? Highest score of any part of your fist face that touches the target board. Then obviously to cheat, you want to have a huge fist face, right now, yeah? So as to have higher chance of getting high score. But of course, you are not appreciated for your marksmanship. It's like, trying to increase your fist. So people will not readily hire you or pick you as a marksman, right? As a person with very accurate, aiming and shooting of the bow and arrows. So the idea is that in confidence interval, we want to calculate the lower limit and the upper limit. Okay, and the way it goes is that it will form a lower limit and an upper limit in this manner. Okay, so straight away you can see that the plus minus x bar plus z sigma over n is going to give the upper limit. X bar, the sample mean, minus z sigma over square root n is going to give the lower limit. And that is one formula if you have a point estimate of sigma, or if sigma is given in the question. For example, the question says, it is known that the population standard deviation of the 200,000 town, the 200,000 town, the population standard deviation of their height is 0.1 meter, so 10 centimeters. Then sigma is known. Sigma is known to be 0.1 meter, and then you can substitute that number into sigma. Another formula, I'm just going to write it down, but it's not really another formula because it's looking exactly like this. But in the case when we don't know sigma, sigma is the population parameter. And if we are really trying to find mu, that means we don't even know very well or don't know the value at all of population mean, much less to talk about population standard deviation, which itself requires population mean to calculate. So typically, all right, in practice, almost all the time, whether it's clinical trial, business profits, weather forecast, game simulation, whatever it is, the sigma is almost always never known, the population standard deviation. Instead, we have sample standard deviation, all right? And in place of sigma, then we will use t, the t distribution. That is the reason why we have to also talk about when should I use t, when should I use z, right? So basically, that's one formula, and we choose one of them, never both at the same time. Typically, it is t. I'll explain, of course, in a while. Now, let's understand this formula first. This formula, first of all, is going to give us the lower limit, let me call it LL. So it's given by sample mean minus, I will just use Z sigma, the first version first, but just keep in mind that uh, your test question exercises may also hide the sigma from you, not give you the value, and instead tell you that the sample standard deviation is 0.1, and then you will use this version. So that's one. And of course, as you can deduce from the formula, that this square bracket, right, this range here, is almost always going to be, not almost always, it's always by definition, right, by construction, centering around x bar itself. Yeah, okay. So it's always centering around x bar itself. And this from center to the edge will be, first of all, symmetrical, equal in the distance, but we don't call it distance, we call it the width. All right, and typically some notations, and this part I need to say some, not a standardized way, but people do call the 2 times width as length. All right, but we seldom ever call it the range of the confidence interval. We might call it the length instead. So the length and the width, it has got some other localized terms to it. It might be called tolerance. It might be called error. It might be called margin of error. And these are more application oriented. I won't say it's colloquial. I also won't say it's really layman. That means we just say it casually. It's more like very application oriented or customized to each usage. For example, in manufacturing specification, in engineering specification, whether it is electrical voltage or the length measurements or the dimensions of the object to be molded or designed, we will say the length of this table is 1 meter plus minus, right? So another one, plus minus, right? Plus minus 1 mm. And that is another more slightly official way is to say 1 meter with a tolerance of 1 mm. Yeah, so if it's electrical voltage, we might say this circuit board is designed to take a DC voltage of 5 volts plus minus 10%. So 10% of 5 volts, right? 0.5 volts. So from 4.5 volts to 5.5 volts, the circuit will be able to withstand the voltage, right? But if you apply a 240 volts on it, you will fry the whole circuitry. And these are the terms typically being used. Okay, so that you recognize it when the exercise question, test question says, the margin of error has to be within 5 minutes. That means minus 5 minutes to plus 5 minutes, yeah, of the sample mean. So that's the idea here. And of course, the way we do it is by sampling. After sampling of n, yeah, the n actually appears inside, right? So the confidence interval depends on n itself. Now we're not done with the descriptions yet. This term and its equivalent Ts over square root n is called the standard error. And it's a very frequent statistical term that you might even see in output printouts of R, Python, even Excel. You might even see this term. And this term is standard error. It always means this particular I'm sorry, I should exclude the Z. I over included it. So this term is not standard error. Whereas without the Z, I should emphasize. So let's correct that. Okay, good. So now you know. So with a contrast, right? So don't over include the Z, because then the standard error will be different whether you choose Z or T, right? So no, it is independent of Z or T over square root n. And yes, so now I should circle carefully. It is this term alone, sigma over square root n. Okay, so this is called the standard error. So sigma over square root n is first of all, it's called standard error, and the meaning is that it is the standard deviation, the population standard deviation of the sampling distribution of sample mean, of X bar, that is, if you recall. Yeah? Sampling distribution of sample mean. That is X bar. In other words, we're trying to say that sigma over square root n, yeah, is the variant, rather the square root of the variance of X bar. Yeah, okay. And another symbol to represent this is the population standard deviation of X bar, isn't it? Yeah, of X bar. That's why sigma and sigma X bar, they are really different numbers and live in different worlds. Sigma is the population standard deviation of the parent distribution. The very sigma lives in the same world, same histogram as mu itself. But sigma over square root n, this quantity has a name. It is actually the value of sigma X bar. So if we say sigma is just sigma X, then sigma X bar is the population standard deviation of X bar, the sampling distribution of sample mean with a sample size of n. We have dropped the suffix n from the X bar. You notice that now, because n is going to be single number. We're not going to generate, right? We're not going to do different experiments where n equals to 3, n equals to 10, n equals to 12, right? If we can afford such 3 experiments, we might as well add them all up and say, let's do a single experiment of n equals to 17. So we are not going to split up our resources into sub-experiments. So that's why n is always a single number in any quiz or exercise questions. Okay, now that we have the sort of names to it, we can also construct some sort of a diagram where this will be X bar. Yep. And the whole idea of X bar is that we have mu X bar, right? Mu X bar. This is supposed to be mu X bar, but mu X bar will, for lack of the ability to know mu X bar. Remember, this is population mean of X bar. We're trying already very hard to find or estimate the population mean of X itself. So why are we trying to give ourselves even more trouble, more work, right? But that's just set to be equal to X bar, little X bar, the sample mean itself. So we are going to point estimate. So at this point, we're going to cut short circuit it and say that, okay, we know mu X bar. It is point estimated by sample mean itself. That makes sense. That makes total sense. Remember, in our sampling video discussion, X bar lives in the world of capital X bar. the random variables sample space and histogram. And so where does X bar sit? It sits, we would make an assertion that it sits in the middle. We make a point estimate of mu X bar and claim without proof, and no one else can also disprove us unless they are richer than us, they have a bigger sample size, they can perform mu X bar with a larger n than us. Okay, then they are presumably more reliable, more precise. Okay, but then at this point, we will only say our X bar is going to be point estimating mu X bar, so it sits in the middle. And the the lower limit, right? So this part is going to be given by X bar minus Z sigma over square root n. And the upper limit, the high limit, did I write? High limit is going to be given by X bar plus Z sigma over square root n. Okay. So in the y-axis, however, is going to be our distribution. Okay, because remember, X bar has a distribution. Right? X bar has a distribution. And the confidence level that is given, for example, find a 95% confidence interval. That 95% will be the confidence level. So this will be our examples 95%. So 0.95. So this is meant by, this is how we get precise or quantify, yeah, the idea of 95%. So this 95% is what we call the confidence level. This is typically given to us. All right. The 95% dictates what's the size of Z. So this is given. We just perform an inverse norm to find Z. And if it is T, then we find an inverse T to find the value for Z, sometimes called the critical value for Z or for T. All right, so this will be the limit. And once we find the Z, because we already have X bar, we have sigma, we have n, of course, right? Then we can calculate first the standard error, then multiply by Z, we get the width, and then we just use X bar plus minus the width, we'll get these two lines. These two lines, these 2 points, these two numbers, together with a repeat of the confidence level, right, will give us the confidence interval. So remember, confidence interval has 3 numbers. So this one will differ. So confidence interval is not a range. It's not a range because confidence interval is made up of 3 numbers. Okay, so I will just give an example first. The confidence interval, allow me to abbreviate as CI, but of course, when you're answering test or exam questions, please spell out in full. Confidence interval, example, confidence interval, what do I want to write? Confidence interval, so 95% confidence interval, right, is from 1.55 meters to 1.63 meters. Okay, so where are the 3 numbers? First number, second number, third number. Now, obviously, we calculate, right? We derive the low limit, the high limit, and kind of like free of charge, we copy the number from the input of the question, right? 95%, because we were told that please calculate a 95% confidence interval given that the sample mean is this and the sample standard deviation is that with a sample size of this, right? So we can do the calculation rather easily because we just follow the formula. That's all. Finish, right? And then when we conclude, we should present always 3 numbers. the 95% confidence interval, right, is from 1.55 to 1.63. Some students, because it's natural to do plus minus, so they do a plus first, they got 1.63, then they do a minus, they got 1.55. Then they write 95% confidence interval is 1.63, 1.55. And strictly speaking, the grader can mark you wrong because that's not the way we represent a range, right? So what's the difference? The difference between confidence interval and range. What's the difference? Of course, the confidence level. But what's so big deal about it? Now, first, common examples of confidence level may be 90%, 92%, 95%, 99, 99.99%. These are common values. So you can notice that it's already on the high side. Nobody will ask you to calculate a 10% confidence interval, 20%, 50% confidence interval for the 200,000 people town height, right? We don't do that. No? So confidence interval typically will be these numbers. And in practice, these numbers, they don't differ by too much. So unless we are talking about super high precision, very critically precise, because if you miss by a little bit, a tiny little atom, then the whole thing is spoiled, like maybe in wafer manufacturing. You need super high precision, not only because the position of the circuits inside that chip is already at the atomic level, or even nowadays they're trying to go into the subatomic level. Not only that, but also you need to be very, very precise because atoms themselves are very complicated, right? So at that level of precision, you need to position the atom very, very accurately. The atoms themselves are vibrating. So in critically precise situations, you might insist on 99.99%. But if you're talking about businesses, then 90%, 95%, more or less, it's about the same. You don't really perceive the practical difference between them. Mathematically, the numbers will look very different, sure, yeah. But in terms of the impact, how it might affect or change even your business decisions, commit or not commit, right? It's not going to have that big an effect to swing your decision from one way to another. Now, why do we then give all these numbers if basically in practice they are more or less 90%, right? Like very, very high. The way to think about it is so the interpretation, the way to read and understand these three numbers is, first of all, we are confidence level percentage sure, right? So use the word sure, use the word confident, but never say there is a 95% chance, right? I'll come to that in a while, right? So we are 95% confident or sure that about what? Remember, we are trying to find mu, so always come back to mu. The interpretation must always link back to mu. We're 95% confident or sure that mu lies within 1.55 meters to or and 1.63 meters. Okay. So as a side, never say we have 95% probability chance. These are all considered wrong, right? That mu is in 1.55 to 1.63 meters. So never say that. Right? So this is a big no, big wrong. Okay. Now that's number one. Number two, what's number two? Number two is, sure, this is the way we read this. We are 95% sure that, mu is somewhere between 1.55 to 1.63. Okay, but it still sounds a bit abstract. So another way to think about or interpret this statement or this confidence interval is to say that if we repeat, right? How many confidence interval did we do when we measure n equals to 20 people's height? Well, 1. Because after measuring 20 heights, that's quite tough. We find the average, we find the sample standard deviation, and then we construct the limits. That's all. And we can only get 1 confidence interval. All right. So if there is this mu is actually 1.6322. Do I have a very brilliant color here? Okay, 1.6322. Something that you are not supposed to know, but I just put it here to give you a visual guidance. Okay, so mu is there. Mu is this number on the x-axis. X bar axis. Then the idea becomes that when we have our interval, that's one interval, right? One of many. One of many. That's our current interval. So n equals to some number, say n equals to 20. So when you do 20 measurements, you get only 1 confidence interval, correct? And we are not going to do a second confidence interval because if we can, we might as well do a single confidence interval with n equals to 40, making our confidence interval very reliable, right? We're not going to break up our resources into 2 halves. But theoretically, thinking-wise, we can imagine that if we repeatedly do this, right? If we repeatedly do the sampling with the same sample size, yeah, same sample size, again and again and again. Now, first of all, the center will shift, agree? Because when we get 20 people's height, some will be averaging to a higher number, some will be averaging to a lower number. And perhaps, yeah, some will be a bit off because we can see this mu's correct position, accurate position. But actually, we don't know whether it's off or on, contain or doesn't contain. Yeah, some will be way off, some will be very fat and yet still way off. Some will be very narrow and short and slim, but did include mu. So the did or did not include mu, let me repeat again, we don't know, right? Because we actually have no idea of this mu's position that I secretly show you. Yeah, and we keep doing that. So if we keep doing that for infinite, that's the best part about mathematics. You can always say infinite very cheaply, right? Like you don't bear the consequences, and you keep doing that, yeah, until infinite number of times. Let's say 100 times. So out of these 100 times, right, and this is a 95% confidence level. So if we did, so the interpretation is that the meaning is that if we did confidence interval of same sample size n infinitely many times, then what happens? If we did only 100 times for a 95% confidence level, we are going to say that 5 of these intervals out of 100 will not contain mu. Or another way to say it is 95 of these 100 intervals will contain mu. So that's the meaning of the 95 here. That's the quantification of the 95. We can count 100 of these intervals, right? And we know that 95 of them, 95 of these 100 intervals will contain mu. Of course, we won't stop at 100 because infinity is cheap, right? So we will say if we did these, maintaining the same n. If you change n, then you know we are not matching up very well. Huh? But if we maintain n equals to 20 and we repeat that, then we are actually getting this distribution. Yeah, and then we'll say that we can conclude that if we did this infinitely many times, then 95% of these confidence intervals will contain mu. However, don't be too happy yet. We don't know which particular interval. Okay, so it's a little bit nearing the quantum physics kind of thing. We don't know which one, although we know very accurately 95% of these will contain mu. We don't know which specific one contains, in particular our actually measured, actually calculated confidence interval. Is that the one that contains mu or not? We cannot know. We are unable to know. Because if we know, and we repeat this frequently enough, we can eventually, we know, oh, this is it, this is it, this is it, right? This contains, this one doesn't contain. That is information telling us that mu cannot be this far right. It has to be a bit left. And now we take the narrowest, we can actually drastically improve mu, isn't it? Yeah. So that would be counterintuitive that we are unable to know mu in a cheap way, and yet we can know mu by deduction, right? By inferring from the knowledge that whether one interval is having mu or not having mu. So we can't tell. We actually cannot know. Okay, but it's good enough, at least in exam, to say that if the meaning of 95% confidence interval is from 1.55 to 1.63, the meaning of that is if we repeat this sampling of sample size n equals to 20 infinitely many times, then 95% of these many confidence intervals will contain mu and 5% will not. Which particular confidence interval contains mu or not contain mu, we have no idea. Okay. Next, I just want to talk about Z or T. Okay, so this is a very important bread and butter issue. So to begin that discussion, I need to replicate my very beautifully drawn X bar. And at that time, I say that I'm just going to shortcut it to X bar itself, little X bar itself. Huh? So knowing that that actually is just a point estimate of mu X bar. Okay, fine. I think I better write this down. Okay, and we calculate the lower limit and the high limit, right? And I was saying that X bar is going to be normally distributed so that we can calculate Z or T. So a sort of a parallel x-axis is either the z-axis or the t-axis, where the center is 0. All right, and we have the z value here. Maybe it is 1.96. Maybe it is 1.64. Depends on you know what's the confidence level we choose and whether you choose Z or T and your sample size. So all these will determine what's the value here. This is an example. Okay. So what's the big deal? The big deal is that in order to get this 1.96 from the given confidence level, we will need to perform inverse function, knowing the probability and or the area. Yeah, we know the area here. We need to calculate the z value or the t value here. So whether z or t, you need the inverse z, inverse normal or inverse t function to calculate it. And that is where we need x bar to be normally distributed or t distributed. Okay, because if we cannot guarantee that x bar is normally distributed, we cannot use inverse norm, inverse like q norm in R or norm dot inverse in Excel. And we cannot perform the calculation or finding of these numbers for t distribution, right, if we cannot be sure that x bar is following t distribution. So when does x bar follow normal? When does x bar follow t distribution? It all got to do with, first of all, is x normal? So is the parent beautiful, right? So is x normal? The parent, is it normal? Is it normally distributed? That means, do we have a bell curve? Do we know that it is a bell curve? We know it is a bell curve if the question says it's a bell curve, right? Or the question allows us to say, assume that the 200,000 town people's heights they are all normally distributed. Okay, fine. Then we just assume. Sometimes we have no choice but to assume, but typically the question will clarify for us. So do we know it's normal? If we know it's normal, yes, right, that's good. So if we know it's not normal, then the question is, then we don't care about the sample size. No worries about n. Because parent is already beautiful. So, you know, hard work is no longer that important. Right? Because parents are already rich, so hard work is no longer that important. Something like that, just to help the memory. Okay, so if we do know that parent is normal, then we don't really worry about sample size. We don't have to ask that question. That means whether sample size is 1 or sample size is 300, it's all the same by asking, is sigma known? That means, is the population standard deviation value given? Sigma known or not means known to us or not. Is it given as a number, as a numerical value that we can enter into Excel, R, or calculator to perform calculation? So known or not is in that sense. Because sigma, that number, always exists. So long as you have a bunch of numbers, those numbers will naturally have a sigma. It's just that, do you have the time to measure all those numbers in the population? It's going to be large. It's going to be 200,000 over measurements, right? So do you have the time and patience and budget and money and technology to go and measure all of them? Then you do the necessary variance calculation, then take square root. So is sigma known or not? Sigma exists or not? It always exists. Is it known to us as a number? That's the meaning. So if it is known, right, then we use z. Yes. Okay. So if it is known, then we use z. Let's check. Normal sigma known, use z. That's correct. And don't care whether n is 1 or n is 100, large or not, statistically bigger than 30 or not, doesn't matter, because it's already normal. So everything is nice, right? Normal means nice in mathematics, and in this case, also in your choice of whether to use z or t. So if sigma known, then use z. If not known, then use t. All right. Use t also when you have data. So when you have data, with most data sets. So for example, if you use R comes with it some standard data sets. Okay, so chick weights, empty cars, and some of the well-known popular ones. No matter what, those data sets, yeah, so those data sets, they are actual measurements, maybe outdated or anonymized, or just to ensure that those data sets are not fabricated ones, faked ones, which will give very bizarre answers. Okay, so they are real, but maybe outdated, not applicable, or not sensitive anymore, and so it's being stored inside the software. So when you use those, we will tend to have to use T, because do we know the population standard deviation of that data set? Obviously, no, we don't have the population standard deviation. So we will end up using T. But, right, we will need to make this quiet and frequent assumption, right, that X is normal, normally distributed. All right, so we have to make this assumption so that we can traverse this path here, you see, with data sets. So just so you understand that for data sets that are given to you, maybe you're asked to download a file from a exam server site. Then you download the file and you wonder, should I use Z or T, right? Here, typically, we'll end up using T. Okay, unless the question specifically explains or asks you to assume that is that population sigma is given, is known, then, but rarely. If you're given a bunch of data in a data file, then you are supposed to be analyzing from scratch, and you will have to make this assumption that X is normal so that you can traverse down. Another point to note is that basically T requires parents to be normal. So you cannot just use T without having a normal parent. Think of T as a spoiled kid. It is a rich family kid. You have to have rich family, rich parents, right? So otherwise, no money to spend. So T has to be or can only be used when X is normal, or when you have reasonable grounds to assume that X is normal without being too absurd about it. For example, are people's height normally distributed? If you say it's normally distributed, you assume it is strictly normally distributed. You're also saying that there's a tiny little chance that a random person, is 6,000 meters tall. Although the chance of it happening is far more remote than the universe suddenly collapsing. But it's non-zero chance. That kind of meaning. So it does sound a bit absurd, but is it reasonable? Yeah, I think people will accept. However, for a Bernoulli distribution, like for example, tossing a coin, it's either head or tail, no other numbers in between. And then you start saying, let's assume that this parent distribution, that means whether head or tail, is normal. Then I think you're getting ready to fail, right? Yeah, very, very difficult, not convincing. So, so just ask yourself those few questions before you come down this track and make those assumptions. Now, what about the other side? What if we don't have normal distribution? So this part, yes, we do. All right. I think we should emphasize that. Very nice. And this part, we don't. Right? So we have something like this. Right? So parent is very non-normal, and you cannot, or else you cannot make the assumption that X is normally distributed, because it is maybe unreasonable, maybe inappropriate, maybe the question already said that X is not normal. Then you say, let's assume that X is normal. Then it's very unreasonable, right? So you're already invalidating the question. So if that is the case, then in this case, we're not going to ask whether sigma is known or not. Okay, we are going to ask sample size, because this comes in a big deal. Right, is sample size known? Is n large? Of course it's known, right? Greater than 30. right? Is n large or not large? If it is large, then we are good, right? So yes, then we will activate CLT. Remember that we didn't have a rich parent, so we got to work hard. N has to be large, right? And we did work hard. So what happens? Well, we didn't have rich parents, so we worked very hard, and CLT guarantees that the child will be normally distributed, right? So the X bar will be normally distributed, which means you can use the Q norm. Also use Z. Maybe use Z instead. So for CLT always gives us permission to use normal distribution, never T. Or you never hear of conclusion saying, since n is large, we use CLT, hence we use T. No such thing. Always normal distribution. Okay, and when n is not large, then what happens? N is smallish, like 10. And we know that X is not normally distributed. If we were told, then we are dead, right? So basically, the question cannot tell you that X is not normally distributed. So assume X is normal if possible, right? That just means that the question did not specifically say that X is not normal, so that we still can exploit that ambiguity and say, okay, assuming X is normal, and then N is small, right? And then we see if sigma is known or not known, and then we come back here. So it may be that we use Z or we use T depending on whether sigma is known or not. So possible, right? And if no, then dead. Then we are dead. Very dead. Okay. Because you cannot use Q norm, inverse norm, QT, inverse T to find the critical value over here. That is very important to find the margin, right, the error, and then to calculate the confidence interval. So I would say exam questions, exercise questions typically won't force you to this corner. But then just so you understand that this corner exists. So just watch out. Now over here, let me explain a little bit. Assume X is normal if possible. What does that mean? If possible means the question just says that, oh, you know what? Download this data file and which contains 20 measurements of randomly selected people from this 200,000 town, and calculate a 95% confidence interval for the height, the population height of this town. So you download the data file, realize that the sample size is 20, not really large, and it does not say if the height of the town people follows normal or not. That is the ambiguity part. So we can exploit that. So that's possible. Can we make an assumption? Yes, we can. So there's no other ways. So when you make an assumption like this, then we are basically starting on the left branch here, and you can then say, well, no worries about the n being small or large, but let's check, is sigma known or not? Well, for the data set, the question never tells you about sigma. Typically, it won't. That's why we measure, right? We don't even know the mu. It's very hard and weird to say that I know the sigma, but I don't know the mu. So if you, in this case, you will end up traversing down this path and use T, which is why I say that oftentimes with downloaded data sets, we end up using here, using T. So don't use Z as your first choice. Other than that, it is also sometimes possible that the question says, here's a data file of 20 measurements of heads and tails, right? And some are heads, some are tails, and that's all. So you know that it's a Bernoulli distribution. Bernoulli is very, 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 very non-normal because it doesn't have you know any similarity to normal distribution. So for Bernoulli, if you start saying that, let's assume that the head and tail follows normal distribution, it's going to be a non-starter in the first place. Basically, that's this corner here. That's this corner. So it will be very weird for an exercise or a quiz question file to say, download this file of 20 head and tail distribution. That will be a very dead corner kind of situation. So one will have to then compute, like we did in the sampling video, the explicit X bar distribution, one by one, point by point, right? Then we can obtain the equivalent non-normal X bar, maybe zigzag or slanted a bit, is skewed to one side. Then we use approximation method, graphical method or whatnot to then reverse out what might be the critical values. So it's possible, it's doable, but that's way beyond most of your syllabus and a need for understanding. Okay, so that's one date call. Okay, so let's just draw the boundaries of our discussion, and we are coming to the last point on the two possible kinds of problems you might encounter, only two, during exercises or exams involving confidence intervals. So the first kind, so the first kind is the obvious one. Just calculate, right? So given C confidence level, X bar, S, T, no, sorry, S and N, right? Calculate or find confidence interval. Given the confidence level, 95%, X bar is 1.62, S is 0.35, N is sample size of 20, right? And assuming that the height is normally distributed, find confidence interval. So whether this is explicitly given or you are asked to download a data file to calculate yourself what is X bar, what is S, or they tell you that the population standard deviation sigma is known to be this, right? So that's fine, no issue, right? So very straightforward. Just follow what we have been doing. Essentially is this formula. So second kind of problem is more for planning purposes, and that is very realistic, very also frequently encountered, is to give width, or in that certain cases we say tolerance, right? Given the tolerance and the confidence level, and the sigma, find minimum sample size n. Minimum because we are given the tolerance, we're given the confidence level, we're given the population standard deviation, right? Find the sample size, minimum sample size that's required to produce a confidence interval that is lesser than this given tolerance. You can err at the most up to tolerance level. You can also err lesser than that. You can also deviate from the mean, within or lesser than the given tolerance. So this will be what I want to discuss a little bit more, all right, now. And recall that on this part of our notes, we say that the whole, this is the width, right? This width is quantified by z sigma over square root n. So what we are going to do is to find z, and basically this is going to give rise to z. Okay, so confidence level is going to give rise to z. So we have z sigma over square root n. N is what we want to find, is equal to tolerance. Basically, it's less than or equal to tolerance. But then I think for now, let's just put equal, which is easier. So we want to find n, and we know tolerance, right? So, or the width, and we just do the exchange. So square root n is going to be z sigma divided by tolerance. And it doesn't take much to see that I just square them. It will be z sigma over tolerance squared. That's all. So what you do is that we will just say n is equal to the next higher integer of this calculation. So z sigma over tolerance squared rounded up. Rounded up. That means do a little bit more work. If the strict calculation results in 76.23, that means 76 sample size is not enough. It will break the tolerance. So you're going to do a bit of fractional more work, theoretically. But it's impossible to do 0.23 sample size. You either take one more measurement or you don't. Yeah. So we'll then do 77. This just means take the ceiling of that 76.23, which means the next integer larger, just the next larger integer than the given value. That's all. So it's actually easier to understand by English. The next larger integer. So round up all the time. That's all. Yeah, and that's it. So find the minimum sample size. You always give the minimum, because the larger the n, the smaller the width, and definitely is acceptable within the tolerance. If I give you this width, this tolerance is 0.5 mm, then the larger the n, the smaller is your actual width of the confidence interval. So it's fine. Right. So if n is infinity, then both your brackets are just sitting around x bar itself, which is super, super precise, very, very accurate. I'm 95% sure that the height is from 1.599999 to 1.60001. I mean, you can already conclude it's 1.6 practically, right? Yeah, so that's a very, very accurate, precise measurement. And so the larger the sample size, the more preferred in practice in any situation, no exception. So, but of course, the larger the sample size, the more work. So let's put that down. Yeah, so when n is large, when n increases, with, that is precision and reliability, decreases, which is good. Right? But no good is cost, right? Cost increases. Yeah, okay, so just to note. So think of n as hard work. N is actually hard work. Appreciate that when, if I were to give you a field exercise and say, okay, next week, please go and randomly perform survey and ask 10 households. Make sure you come back and do your analysis. Okay, so sample size is 10. Then you and your group mates will start to discuss, maybe distribute work, this and that, and it's still doable, right? The next moment I say, sorry, I forgot. We should make it 50 households, not 10 households. Immediately, right, you can appreciate that. Oh no, right, you will start to want to negotiate. Right? How come there's this big tariff being imposed on us? Yeah, so that you can feel the hard work, the hardship between doing interviews for 50 households and doing interviews for 10 households. Definitely different level, right, of work and effort. So n, when we just calculate, oh, n is 70, okay, fine. Oh, n is 6,000, fine. Just write down as an answer. I will also ask you to appreciate that in real life, n going up, going down has real implications, right? It is actually n that is converting theory into real life impact. If your minimum sample size n that you just calculate on paper very easily, right, ends up being 1,000 versus another calculation that ends up having n being 20. Now that is going to have a very huge impact in terms of, financial budgeting, personnel, uh, technology even, right? Because for n equals to 1,000, we are talking about high precision and high speed machines or sensors or measurements or instruments that are typically more expensive. But if n is 20, then maybe manual measurement might be sufficient. So in some sense, for example, in Singapore, we have those ERP systems that automatically click, 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 and money goes into government bank, right? Whenever the cars pass through the gantries that are positioned around usually, right, busy districts, starting with the central business districts, and then increasingly other parts of Singapore might become busier, and then you can also add, or government can also add the ERP gantries there, so that whenever cars pass by, they will sense it, right? They'll sense the reader installed in each car and then charge accordingly. Now, if the speed of cars passing through those ERP gantry sensors is very high, yeah, and you don't want some cars to miss being detected just because the speed is very high. Then once this is known, everyone will be speeding past the ERP, and the sensor is too slow to pick up those signals. So 1 out of 5 cars will be charged. The rest will escape paying the tax. So that's not fair and not good and not the right way, yeah, to tax people. It's like you struck the lottery of being charged with the ERP, electronic road pricing tax. And so you need a high speed sensor when the speed is high. The speed of the traveling cars are high. Then you need very high speed and high precision. It won't miss. It is far more capable. You can like double the quantity of cars, even though they travel slow and high speed. The sensors can detect, can manage, can have the capacity to capture each and every car without missing, even if it is running away from police and traveling at 200 kilometers per hour. The sensor can pick up. You need that kind of sensors, measurements, instruments, and of course, the more precise and more sensitive the sensors, the more expensive, right? So then in order to not over purchase, right, and then underuse, and then wasting taxpayers' money, and also not having too low a specification such that some cars are known to be able to escape paying the ERP, right? Then, of course, the Land Transport Authority, the government body in charge of this, they will have to perform some field experiments to ensure that they are buying at the right level of precision. Yeah? So that's basically also, in some sense, involving the sampling of the cars. And perhaps the instruments can actually be so fast, so accurate, so precise that it can sample 3 or 4 times the car. I mean, it's sampling so rapidly that the car, even though it's moving at 120 kilometers per hour, to the sensor, it is momentarily stationary. It's as if it's not moving too much. And within the next millisecond or microsecond even, the car just moved another 10 centimeters only, even at that high speed. Then the sensor is able to kind of read at its own slow pace, easy pace, right? Because it is very capable. It has high speed sensor and CPU to process all the signals before the car even moves 10 centimeters. And that would allow the sampling to be done very reliably. So even if there's electronic interference, the sensor will try to read the car n times, like 4 times. Out of 4 times, maybe be due to strong interference, maybe from the sun, maybe from an airplane flying past, maybe from an accidental drone flying past, whatever it is, 2 out of the 4 times reading and measuring the car's entry, the vehicle ID number and all that, failed. Only the third and fourth time were successful. And so then the sensor and the processor inside can read these samples and then process the successful ones, right? So again, large sample size means higher CPU, higher specs CPU, higher speed processing and everything, right? So naturally those machineries will be more expensive, right? So what kind of N are we talking about? So even if it's electronic, where having N equals to 5 or 500 is quite easy, right? Because you're not forcing manual labor to do the job. It does impact real life because it will involve paying more for the higher capacity, higher speed electronics and everything. Yeah. So N is actually the bridge connecting to the real world. So don't get lost in all the calculations and theories, because typically the exercise and questions given, N is the first input, right? So sample size is 5. It's already there, right? Like given, and very silent, very inconspicuous, very unimaginative, and seems to be quite harmless. But this is the most impactful number as far as real life is concerned. All right, just to give you that reminder before I finish up this video. All right, that's all for this discussion. Thank you very much for your attention. See you in the next video.